Welcome to section 10.5. In this section, we're going to rationalize denominators and numerators of radical expressions. So some of you may or may not have done this before. It just depends on maybe whether in school your teachers taught this to you or not. Some teachers consider it important, others don't. Now, as far as simplification goes, it's really not that important, just for doing it for the sake of simplifying. However, this technique, or these techniques that we're going to learn in this section, are actually completely necessary when you take, or if you ever take calculus. You have to use these techniques in order to find some things that you'll do in there. So that's really, I guess, the ultimate reason for why that we are learning these and how to rationalize. Okay, so a lot of people would say, like right here, that this is not simplified, 7 divided by the square root of 2. And that's because it's considered unsimplified because there's a radical in the denominator. Okay, so to rationalize means to rewrite an expression without a radical. So if you're going to rationalize the denominator, that means to rewrite it so that the denominator does not have any radicals. Or you could rationalize the numerator, which means to rewrite it so that the numerator does not have any radicals. Okay, so there's some tricks for doing this, and once you learn the tricks, it's pretty easy to go from there. If you have a simple radical like so in the denominator, and the goal here is to rationalize the denominator on these next several problems, okay, the trick is to multiply by a fancy form of 1. Remember, you can always multiply an expression by 1 because that does not change the value of the expression. And the form of 1 that I'm going to multiply by is this, radical 2 over radical 2. Now that's equal to 1, okay, but by multiplying by that, it's going to help me eliminate the radical in the denominator. So then in the numerator, multiplying across these two numerators, we would have 7 times the square root of 2. And in the denominator, I'll write it out here, we have the square root of 2 times the square root of 2, which you already know, that's the square root of 2 squared, which is 2. So see, we have now written it as an equivalent expression, but this one does not have any radicals in the denominators. Okay, so that is the trick. If you just have a single radical and you're trying to rationalize the denominator, you would multiply by that radical over itself. Okay, so on this one, the fancy form of 1, let me write that out here. This thing is equal to 1, so we didn't change it. That we would multiply by, if we're trying to rationalize the denominator, would be that denominator over itself. So we would multiply by the square root of 16y over the square root of 16y. Okay, in which case we would have in the numerator, we would have 2 times the square root of 9. Well, the square root of 9 is equal to 3, so let's just write it as 3. And then times the square root of 16y. Over, in the denominator, we have radical 16y times radical 16y. So those radicals cancel. Let me write it out though so you can see. That's really the same thing as radical 16y squared. So the radical and the square cancel, but we are left with an absolute value because 2 is even. So in the denominator we're going to have absolute value of 16y. And in the numerator we have 6 times, now here the square root of 16, that's equal to 4. And then we still have that square root of y there. Okay, simplifying here, we have we can pull this 16 out of the absolute values. So we have 24 times the square root of y divided by 16 times the absolute value of y. 24 divided by 16, let's see, we can take a 4 out of both of those. 24 divided by 4 is 6, 16 divided by 4 is 4. Actually, it looks like we could have taken an 8 out of both of those because that can keep reducing to 3 halves. So we end up with 3 radical y over 2 times the absolute value of y. Okay, what would have made this one slightly easier here, oops, give me a second, is if we had simplified before we rationalized. So if we had done that, we could have said, oh, look at this. Square root of 16 is equal to 4. And square root of 9 is 3 too. But we could have simplified that first, and we could have said, well, then this is equal to 2 times 3, or 6 in the numerator, divided by 4 radical y. Now, if we had done it that way, then we would have only needed to multiply by radical y over radical y to eliminate the radical in this denominator. So we would get 6 radical y over, down here, radical y times radical y is the absolute value of y. And then that's times 4, which simplifies to 3 radical y over 2 times the absolute value of y. Okay, a lot of times people will just leave off these absolute values. My math lab may accept your answer without the absolute values. I'm not certain. If it does, that's fine. Most people would just leave them off because it's a technicality. But I'm going to keep doing it because it is technically the correct way to do it. Okay, let's do another example. Again, here we're rationalizing the denominator. Okay, now if you look at this, we have a cubed root of a fraction. So we don't even have it written as just an overall fraction yet. So first let's write this as a one big fraction by splitting up the radical into two pieces, the cubed root of 2 over the cubed root of 25. Now we can rationalize the denominator. Okay, now this one is a little bit different because it's a cubed root. So if we try the previous technique, and if I try to multiply by the cubed root of 25 over the cubed root of 25, then what we get in the denominator is cubed root of 25 times cubed root of 25. Well, that's equivalent to cubed root of 25 squared. Notice the cube here and the square do not cancel because they're not the same. So we're still left with some radicals in the denominator. So that method does not work, multiplying by a cubed root of 25 over cubed root of 25. Instead, we need one more cubed root of 25 to make that into a 3 so that the cubed root and this cube would cancel. So instead of multiplying by cubed root of 25 over cubed root of 25, let's multiply by the cubed root of 25 squared over itself. And remember, you can only multiply by 1, so you always have to multiply by something over itself. Okay, then in the denominator we would have cubed root of 25 times cubed root of 25 squared. So then we have the cubed root of 25 cubed. And in the numerator we have cubed root of 2 times the cubed root of 25 squared. Now I'm going to write this square right here on the inside of the radical. That way I can, in the next step, I can combine these two radicals into one. Okay. Actually, before I do that, I'm going to simplify though. But in the next step, let's look at the denominator first. Cubed root of 25 cubed. The cube and the cubed root cancel because 3 is even. There are no absolute values, so we just get 25. And the numerator, we have this cubed root of 2, and it makes more sense to simplify this one first before multiplying it together. Cubed root of 25 squared. I know that that will simplify because 25 squared is equivalent to 5 to the 4th, right? Because 25 is equal to 5 squared. So let's write that out. We have, actually I'm going to do this one off to the side. So cubed root of 25 squared. 25 squared is equal to 5 squared all squared, which is 5 to the 4th. So I really have 4 5s under there. So the cubed root of 25 squared is equal to the cubed root of 5 times 5 times 5 times 5. 3 of those 5s I can pull out into a single cubed root. So we would have cubed root of 5 cubed, which is 5, and then we're left with a single other 5, cubed root of 5. So then this, bringing that back over here, that becomes 5 times the cubed root of 5. And then from here we're just simplifying. We have rationalized the denominator, so we have done what the directions say. Now we're just going to simplify. We can simplify this 5 divided by 25. That would become 1 over 5. And we have cubed root of 2 times cubed root of 5, so we can write that as cubed root of 10. So we have the cubed root of 10 all divided by 5. So with cubed roots, you have to multiply by 2, or the cubed root of something squared, so that you end up with a cubed root all cubed, and then those cancel to eliminate the radical. Okay, in this next example, again we're going to rationalize the denominator. Now this one is a square root, so we're going back to the previous method of multiplying by a square root over itself. But first we've got to write it as a big fraction, so we need to split up this radical into two radicals. How about the square root of 5m over the square root of 11n? And then the form of 1 that we could multiply by would be that denominator over itself. And so in the numerator we have, neither of these radicals is going to simplify by itself. So I'm going to go ahead and multiply them into one big radical, square root of 55m times n, all divided by, we have radical 11n times radical 11n, so those cancel and we're left with the absolute value of 11n. And I'm going to pull that 11 out of the absolute value for simplification. Square root of 55 will not simplify because it factors into 5 and 11, which are both primes. So that's it on this one. Okay, now technically here, let me go review these absolute values. The reason why most people would leave them off is because here in the original problem, this is like another one that we did, obviously, and well, no, actually in this case it's not true. I was going to say obviously, if you look at this one, if this had been the original problem right here, m and n would both have to be positive anyways for this expression to be defined. Otherwise you couldn't take the square root. And if m and n are both positive, then you don't need these absolute value bars down here. However, that's not true. M and n could both be negative, and this expression would still exist because you would have a negative divided by a negative. They would cancel, and you would still have the square root of a positive number. So the absolute value bars are actually necessary in this particular example. However, if you go up to this example right here, we have the square root of 16y in the denominator only in the original expression. And so in order for the original expression to be defined, or in other words, its domain, is that y must be greater than or equal to 0. Well, if y must be greater than or equal to 0 for this to exist, then obviously no absolute value bars are necessary over here. So you could just write it like that because the domain is already y greater than or equal to 0 anyways. Okay, let's do another example. And this one we have the fifth root, so a little different here. Fifth root of a squared over the fifth root of 32b to the 12th. Okay, and we're rationalizing the denominator still. Don't let that 12 throw you off because only the b is getting raised to the 12th power. The 32 is not. So we have a fifth root in the denominator. So in order to get rid of this, we're not going to multiply by fifth root of 8. Oops. We're not going to multiply by the fifth root of 32b to the 12th over itself. Okay, because as we learned from the one with the cubed roots, that will not eliminate the radicals because here in the denominator we would have fifth root of this times fifth root of this, which gives me fifth root of that squared. Oops. And then right here we would have, that would be squared because we've only multiplied by itself twice. Instead of a square here, we want to have a 5. So if we want this to be a 5, then we need to multiply by the fourth power and the fourth power over here. Now we have the fifth root to the first power times the fifth root to the fourth power, which gives us the fifth root to the fifth power. And then in the numerator we have the fifth root of a squared times the fifth root of, I'm going to put this 4 on the inside of the radical so that we can maybe simplify a little bit. So we would have 32b Actually, that's not even necessary. 32b to the 12th, all to the 4th. It isn't necessary to put the 4 on the inside because 5th root of 32 already simplifies, and so does the 5th root of b to the 12th. So we'll simplify that first in the next step. Okay, in the denominator, the 5th roots cancel. 5 is odd, so no need for absolute values. So we have 32b to the 12th in the denominator. And in the numerator, we still have that 5th root of a squared hanging out. And let's see, let's just simplify what's inside there before we raise it to the 4th power. Okay, so simplifying that, let's come over here and do some scratch work. 5th root of 32 is 2, I mean. So I'm going to first split this up into 2 radicals. 5th root of 32 times 5th root of b to the 12th. So that's 5 times the 5th, when did I say 5? Hold on. So that is 2, 5th root of 32 is 2, times the 5th root of b to the 12th. Let's split up that into the 5th root of, how about b to the 5th times b to the 5th, and then if I do that, that's 10 b's, so I'm left with 2 more, so times b squared. Then the 5th root of b to the 5th is b, and then this 5th root of b to the 5th is b, so we have b squared, times the 5th root of b squared. Okay, so let's bring that back up here to give us times 2 times b squared times the 5th root of b squared. And let's see if anything else simplifies from here. Now we have 2 over 32, so that simplifies to 1 over 16. And b squared over b to the 12th, 2 of those b's cancel, giving us a b to the 10th in the denominator. And I think that's about it. We can also combine these 2 radicals into 1 because they're both 5th roots. So that would become the 5th root of a squared times b squared all over 16b to the 10th. Okay, so there's some good practice there in rationalizing denominators. You can do the same thing with numerators, of course, and let's go ahead and skip down here and do that first before we do the next part. Okay, rationalizing numerators, if you just have a single radical, the trick is the same. So for right here, say you want to rationalize square root of 18 over the square root of 75. You know, at first I would try to simplify these 2 radicals because that will help to keep all the numbers a little smaller, which just, to me, makes it easier to work with. So let's see if either of those simplifies. 18 divided by 2 is 9, divided by 3 is 3. Okay, so that one simplifies. And 75 divided by 5 is 15, divided by 5 is 3. So that also simplifies. Okay, in this case, 18 would become 3 radical 2, and 75 would become 5 radical 3. Okay, so simplified, that's what we have. Now we want to eliminate the numerator, the radicals in the numerator on this one. So the only difference is instead of multiplying by the radical that's in the denominator, which would be, if we're rationalizing the denominator, it would be radical 3 over radical 3. But we're not, we're rationalizing the numerator. So we multiply by that radical over itself. So we multiply by radical 2 over radical 2 in the fancy form of 1 to get 3 times radical 2 times radical 2 is 2. Divided by 5 times the square root of 3 times the square root of 2 will become the square root of 6. So simplified, we get 6 over 5 radical 6. And that has no radicals in the numerator, so the numerator has been rationalized. Okay, let's work the next one as well. And this next one, we have cubed root of 3a over the cubed root of 7b. Neither of those is going to simplify, so let's go ahead and multiply by our fancy form of 1. Okay, which should be cubed root of 3a all squared, so that we'll end up with 3 of them. So we have in the numerator the cubed root of 3a cubed, and in the denominator we have the cubed root of 7b times the cubed root of 3a all squared. And this time, because the cubed root of 3a does not simplify, I'm going to go ahead and write the square on the inside. That way in the next step I can combine these two radicals into one. Okay, up in the numerator, cubed root and the cube cancel. 3 is odd, so no absolute values. So we just have 3a over, and now let's combine these into a single radical, which would be the cubed root of 7b times 3a all squared is the same as 9a squared. Now I can already tell that when I multiply the 7 and 9 together, I'm not going to get a number for which I can simplify a cubed root because 7 is prime and 9 breaks down into 3 times 3. So there's not going to be 3 of any single factor. So we can just go ahead and multiply those together to get 3a over the cubed root of 63. Now typically you write the letters sort of in alphabetical order, so I'm going to write it as a squared b. Okay, we'll come back to do this one after we learn the next trick we're going to learn. All right, and that is how to multiply or how to rationalize denominators when there's a sum or difference of two terms. So notice in these three examples we have a sum. One of the terms has a radical, but they don't both. Down here we have a difference, but there's two different radicals. And down here there's a difference with just a single radical. Okay, if you have two expressions, or if you have an expression like that, the trick is going to be right here to multiply by the conjugate of the denominator over itself. What's the conjugate? Conjugates look like this. A plus b and a minus b are called conjugates of each other. It's just where you change the sign in between the two terms. Okay, you don't change the sign within the radical, you change the sign between the two completely separate terms, from a plus or to a minus or vice versa. So down here, the trick to getting rid of all the radicals in the denominator would be to multiply by the conjugate of the denominator, which would be 2 radical 5 minus 1 over 2 radical 5 minus 1. Of course, you have to multiply by a form of 1, so these have to be the same. So the only thing you change here is this plus changes to a minus. Okay. And then we multiply it through. Now, it might help if you add parentheses in because you don't want to forget to distribute, and in the denominator you have to actually FOIL. We have two terms, two binomials being multiplied. So in the numerator, don't forget to multiply that 3 out over both terms, and in the denominator, we'll FOIL there. So in the numerator, we have 3 times 2 radical 5 will give us 6 radical 5. And then 3 times negative 1 is minus 3. Divided by, and the denominator, the first two terms are 2 radical 5 times 2 radical 5. So 2 radical 5 all squared because we're multiplying by itself. The outside terms are 2 radical 5 times negative 1, so minus 2 radical 5. The inside terms are positive 1 times 2 radical 5. And the last two terms give us a minus 1. Okay, when you multiply by the conjugates, it will always be the case that these middle two terms will cancel. That's why we multiply by the conjugate, because by those two middle terms canceling and this first term getting squared, we're able to eliminate all the radicals. So in the numerator we have that, and the denominator, let's see, if we square this out, we have the 2 squared and the radical 5 squared. 2 squared is 4, radical 5 squared is 5, and then we have this minus 1 over here. So let's keep simplifying. We have 6 radical 5 minus 3 over, this is 20, minus 1 is 19. Okay, and a lot of people probably would not have distributed in the numerator. In fact, I probably shouldn't have, because what if 19 had a factor of 3 in it? If it had a factor of 3, then it would simplify with this 3, but I would need to first refactor out of 3. So for example, if this had ended up being 18 instead of 19, I could simplify further by factoring out of 3 that numerator first and seeing if it canceled. Okay, so that's how you rationalize the denominator if it has two terms and one or both of those has a radical in it. Okay, in this next example, again, we're going to rationalize the denominator. So we'll multiply by the conjugate of the denominator, which means change that sign. So the conjugate would be radical 3 plus radical 2 over itself. And then we multiply it all out. So don't forget to distribute, add parentheses if you need to. Got a lot of foiling to do here. So in the numerator, we have radical 5 times radical 3, which is radical 15. The outside terms are radical 5 times radical 2, that's radical 10. Inside terms are 3 times radical 3. And the last two terms are 3 times radical 2. And in the denominator, we have radical 3 times radical 3, which is going to be 3. Now, again, the outside terms and the inside terms, if you look, they're going to cancel. We have radical 3 times positive radical 2 minus radical 3 times radical 2. Those cancel, so I'm just not even going to write them. Then the last two terms are negative radical 2 times radical 2. Radical 2 times radical 2 is 2, so we have minus 2. Okay, we have definitely simplified the denominator. There are no more radicals there. In fact, 3 minus 2 is equal to 1. So this is all going to be over 1. So I'm just going to write it without a fraction since it's divided by 1. And let's see, we do not have any like terms in the numerator because these are all different radicals and none of those radicals will simplify. So we just end up with radical 15 plus radical 10 plus 3 radical 3 plus 3 radical 2. And that is it with the denominator being rationalized. In fact, we don't even have a denominator anymore. Okay, and in this last example, to rationalize the denominator, make sure you're pausing and trying these on your own first, as always. We'd multiply by the conjugate of the denominator, which would be 2 plus radical x over itself. So in the numerator, this time I'm not going to distribute. Don't forget parentheses though. So we'll have 4 radical x times 2 plus radical x. I'll distribute at the end after I see if anything in the denominator is going to cancel with that 4. That's why I don't want to distribute yet. In the denominator, after you FOIL, you'll end up with 2 times 2 is 4. Outside and inside terms cancel. Then the last two terms are minus radical x times positive radical x. So that would be minus x. And I don't need the absolute values because the domain of the original problem is x must be greater than or equal to 0 anyways for this to exist. So if x is greater than or equal to 0, then the absolute value of x is just x. Okay, and it looks like nothing is going to cancel because I have that minus, so those 4's do not cancel because the denominator is not factored. So that's it. You could leave it like this, or you could distribute that out in the numerator. Now let's see what happens if I do that. Then I would have 8 radical x for my first term. And then 4 times radical x is just going to be plus 4x over 4 minus x. So those are both good answers there. Now let's use that same technique to rationalize this numerator. Okay, so the only difference is you would multiply by the conjugate of the numerator over itself. So we would multiply by radical x minus 5 over itself. Then foiling here in the numerator, we would get radical x times radical x is x. Outside, inside terms cancel. The last two terms give us minus 25. And in the denominator, we have 3 times radical x minus 5. Nothing is going to cancel with this 3, so we could leave our answer like that. Or you could distribute out that 3 and to get 3 radical x minus 15. Okay, so why would we want to rationalize denominators? Okay, this is where this originally came from. Although these techniques, like I said, are used in higher level math classes that you'll need to know when you get there. But this is the original reason why most people rationalize and why a lot of teachers will tell you rationalizing the denominator is important and necessary because otherwise it's not simplified. Okay, here's why. Imagine you don't have a calculator and you're in 1930s, right? You have no calculator and you're trying to approximate this number, okay, without a calculator. And all you know is that you can look up in a table in the back of a book and you can, from that table, determine that the square root of 2 is about 1.4142. So without a calculator, you would have to set up a long division to approximate this number, 7 divided by square root of 2, so you would probably have to write it as 7.00000. And then out here you were dividing by the square root of 2, so you would divide by 1.4142, however many decimals you take it out. Now this to me looks very, very hard to do. In fact, that would be virtually impossible. Just leave it at that. So instead, if you rationalize first, so if first you rationalize, you would get this. Okay, it's fairly easy to multiply 7 times this number. That doesn't take too much work. Okay, so you would multiply 7 times 1.4142 and you would get whatever you'd get for that out here. 7 times square root of 2. And then out front you were just dividing by 2 now. So now it's going to be a lot easier to divide all these numbers by 2 by hand than it would be to do this. So that's why people originally rationalized denominators. I don't care if you have a simple something like this first example we did, 7 divided by square root of 2. To me, that's a perfectly good answer because today we do have calculators, and so I just say that's fine. But you need to learn these techniques, so make sure you can rationalize denominators and numerators of any of these types that we have done here today. That's it for section 10.5. Tune in next time for section 10.6.